Hello everyone, welcome back to Networks class. Last time we did the following. We took a look at an example of running BFS on a graph and some of the properties of the breadth first search algorithm. And then we continued on to look at a different graph search, so depth first search. So we took a look at an example of that and some properties like the running time, etc. But one thing that happened yesterday was we got to talk about the shortest path property of breadth first search, but I didn't tell you about an interesting property that depth first search has. So the plan for today is to just start off by telling you about this interesting property that depth first search has. And then after we finish that, we'll continue to look at some applications of graph search, which are basically other problems that these search algorithms help us solve. So let's just begin by looking at this interesting property of depth first search. So when we were discussing yesterday, just from the definition of depth first search, we know that every node reachable from S is colored black before S is colored black. And that's because of the fact that DFS uses a stack, right? So the first thing that we do on this stack is put in S, and then we might put in some other nodes. But the very last node that gets popped off, as we kind of backtrack and we're popping things off, the very last node that's going to get popped off before the end of the algorithm is S. So that's why every node reachable from S gets colored black before S gets colored black. But really, this is a more specific statement of a more general theorem. So sometimes people call this the white path theorem. And the statement is the following, that let's consider two nodes. Let's say U and V. If there exists a white path from U to V when U is colored gray, then DFS will color V black before it colors U black. So there's a lot of words. It's kind of a complicated statement here, but I think a picture really clarifies what this means. So here's a picture of this theorem. So here's DFS. So we've started at S, which is maybe right here. And let's say that there's a gray path. And then maybe DFS went over here and colored some things black. So this stuff is black. And then, some more gray. And maybe it went over here and colored this stuff black. And then right here is U. So this path from S to U is gray. And at that point, if there's a white path from U to V, so if there's this white path from U to V, then V is going to get colored black before U is colored black. And that's again for the same reasons as before, because there's this stack, and so DFS is going to go around here exploring things, and whatever it does, eventually it's going to get to V, color V black, and that's going to happen before U gets popped off of the queue. So our statement about S earlier up here is just kind of a more specific version of this. So the statement about S just says this, that at the beginning, S is the only node that's gray. And so every other node here, there's a white path from S to those nodes. And so those nodes are going to get colored black before S gets colored black. So this original statement is just a special case of this theorem. So this theorem is relatively straightforward to prove. We're not going to get into the details, but we're going to see how it's useful in just a moment. And probably the best way of seeing how it's useful is by taking a look at our first graph search application. So our first graph search application is identifying a cycle. So what's the basic problem here? So the problem is that we're given a graph, a directed graph G. So it's directed. And kind of our goal here is the following, that we either G has a cycle, in which case we have to return one, or G has no cycle, and we have to say that it has no cycle. So let's see how we might go about solving this problem by just seeing how DFS behaves on a cycle. So here's an example. So here's a small cycle. And let's say that we're running DFS on this cycle. So we start at the node S right here. And so the first thing that's going to happen is S gets turned gray. And then this node is going to get turned gray, and then this one, and then this one, and then this one. And eventually this node is going to get turned gray. And then DFS is going to see this edge that's between a gray-gray node. So DFS sees a gray-gray edge. Okay, so DFS saw this gray-gray edge. Let's see what happens in maybe a slightly more complicated example. So maybe here's S, and there's maybe some distraction here, and maybe some distraction here. And then over here, there's some cycle. So when we run DFS here, it's going to turn this gray. So this is gray, gray. And maybe it goes down here and gets distracted, and eventually this stuff becomes black. And then it's all gray right here. And then at some point, this node is going to become gray. And when that happens, this node is going to become gray, this one is going to become gray, this one, and then DFS is going to see this gray-gray edge. And so that's the basic idea of how we're going to identify cycles. So the idea here is that if DFS sees a gray-gray edge, then the graph has a cycle. Otherwise, the graph has no cycles. So let's see why that's true. So imagine that this cycle is somewhere in the middle of a big, complicated graph. So it's in the middle of this big graph. Eventually, so at the beginning of the DFS call, all these nodes are white. And at some point, eventually, DFS is going to end up at one of these nodes. Let's say this one. So it turns this node gray. But now, because of the white path theorem, we know for a fact that this node, which is reachable by a white path from the gray node, is going to turn black before the gray node turns black. So eventually, this node is going to become gray, which is going to show us this gray-gray edge. And so because of the white path theorem, we can use DFS to basically identify if a graph has a cycle. So what's the idea here? We're going to run DFS, and instead of just checking for white successors, so just check for gray successors also. So as we're checking for white successors and we're adding things onto the queue, we're going to be looking to see if there's a gray successor, and if there is one, then we're going to say that the graph has a cycle. But the question is, originally that we posed over here, is that if we have the cycle, we also have to return it. So the question is, how can we identify the cycle once we found it? So let's think about that for a little bit. So imagine that this is the DFS data structure queue. So at the beginning is some node. So there's a bunch of nodes here, and at the very back is S, because that was the first node that got put on. Now remember that these nodes are the only nodes that are gray in the whole graph. So all of the other nodes are either black or white. And because of the way that DFS works, we actually have edges between these nodes, because each node was put on here because it was a white successor of the node previous to it. So this queue is actually giving us a path from S to the very front here. Now when DFS sees a gray-gray edge, it must be seeing that edge emanating from the front, because it's looking at successors of this first node. And that gray-gray edge could point to any part inside the queue. So maybe it points to this node right here. And that allows us to identify the cycle. So the cycle that we can output is this cycle right here. So that's a cycle. We know for a fact that all of these edges are in here because that's how those nodes got added. And then the gray-gray edge completes the cycle. So this is the cycle we return. So DFS can identify cycles, but what about BFS? So can BFS identify a cycle? By looking for, let's say, gray-gray or gray-black edges. And the way that you would go about answering a question like this is just by providing an example. So let's show an example where BFS would say that there is a cycle because it sees a gray-gray edge, but there's actually no cycle. So here's an example. We'll start with a node S. So this graph has no cycle, but what's going to happen is at the beginning this node gets turned gray, and then these two nodes are going to get added onto the queue, and then S is going to get popped off, and then at this point BFS is going to see this gray-gray edge. So BFS sees gray-gray, but this graph has no cycle. So we can't really use BFS to identify cycles in the same way that we can use DFS. So one more question about identifying cycles. So what's the runtime of identifying a cycle? Well, to identify a cycle, all we're doing is just this single DFS call. And the only thing we've added is we're just looking for if one of the successors happens to be gray. But we have to look through all the successors anyway, so the runtime of this is exactly the same as a single DFS call, which is O of n plus m. So it's very fast to identify cycles. In fact, just as fast as running DFS on its own. So let's take a look at our next application for graph search algorithms. So this application is called topological sort. And the idea behind this problem is the following. So we're given a set of tasks. So you can imagine these as tasks A, B, C, D, and E. And we're also given some precedence relationships. And what I mean by this is relationships like C must be completed before A, say, just for example. And so it's quite natural to construct a graph. So we can make a graph from the tasks and relationships. So here's an example graph that we might have. So we might have task E, A, B, D, and C. And then maybe we have these precedence relationships here. So something like this, like that. And then maybe something like that. And let's add one more. Okay, so those are our precedence relationships. But what we're looking for, kind of our goal here, is to find an ordering. So find an ordering. So what would be a good ordering? It would be something like this, maybe CB, ADE. And in this ordering, the property that we have is that all the precedence relationships are satisfied. So it gives us a sequence in which we can execute the task. So if I execute task C first, then B, then A, then D, then E, I'm going to be satisfying all of the precedence relationships. So when somebody gave us all the tasks and the precedence relationships, they gave it to us as a kind of this big jumble, and our goal is to pull out this nice ordering. But an ordering may not exist. In particular, it will not exist if there's a cycle. So if I have something like A, B, C, D, and I have precedence relationships like this, then I know I can't find such an ordering because there's kind of a cyclic precedence relationship. And so we're going to be able to identify this as we're running this algorithm. So to specify this more formally, let me introduce a definition. So the definition here is the following. A topological sort of a directed graph is a linear ordering of the vertices such that all edges go from left to right. So that's exactly what we had in this picture previously. In our ordering here, we just had a linear ordering of the vertices and all the edges just went from left to right. And if that's the case, we can just execute the tasks sequentially. So the following is true, that if a directed graph has a cycle, it has no topological sort. But the reverse of that is also true, that if that every directed acyclic graph has a topological sort. So the word acyclic here is kind of self-defining. It just means that it has no cycles. And in fact, directed acyclic graphs are so common that people usually just abbreviate this as DAG. Okay, so let's figure out a algorithm for finding a topological sort if one exists. So here's going to be our algorithm. So topological sort, and it's just going to take in as an input a graph G. It doesn't need a node the same way as DFS or BFS, because all that we're getting is this jumble of tasks and precedence relationships, and we just want to output the good ordering of them. So the algorithm works like this. Initialize all nodes to white. We're going to initialize an empty list that, let's just call it answer list. And then we're going to enter a loop. So while there is some white node, we're going to do the following. You're going to pick any white node S, and then we're going to run DFS on the graph G with the node S, with the following changes. The first change is that we don't reinitialize nodes to white. And the second change is that when a node is turned black, add it to the front, by which I mean left of answer list. So let's be a little bit more clear about this. So what I mean by don't reinitialize the nodes to white is that we might be doing this while loop multiple times. So we do it once, maybe there's some white nodes left, and so we do it again. And the second time we call DFS, we're not going to change any of the node colors. We're just going to leave the node colors as they were left by the first call of DFS. And I think that's going to become clear in a little bit when we do an example. So let's try to take this graph that we had as an example here and try to run topological sort on it to see how it works. So that's our starting graph. And the first thing that we do is we initialize all nodes to white. And then we make answer list be just an empty list from the get-go. And at the beginning of this algorithm, so right here we've entered this while loop. So while there's some white node, so all nodes are currently white, so we're still good to go, we can pick any white node that we want, and then we're going to run DFS on that white node. So I'm allowed to pick any white node that I want. So let me just pick node A. So let's run DFS from node A very quickly. So here it is. So DFS is going to turn A gray, and then it's going to look for white successors of A, and D is a white successor, so it's going to turn D gray. Then it's going to look for white successors of D, which is E, so it's going to turn E gray. And at this point, it's going to look for white successors of E, but E doesn't have any white successors. And so it's going to start backtracking by popping E off of the queue, so E is going to get turned black. And then it's going to be back at D, and it's going to say, are there any white successors of D? And there aren't, so D is going to get turned black. And then it backtracks to A, and A also doesn't have any white successors anymore, and so it's going to get turned black. But as we did all of this popping, as we're turning these nodes black, we should have been adding them to the answer list. So first, when we turned E black, we added it to the answer list. Then when we turned D black, we added it to the answer list. And then when we turned A black, we added it to the answer list. So that's what answer list looks like after our first call of DFS. In our next call of DFS, we can pick any of these nodes. So let's just, for the heck of it, let's pick node C. So we pick node C, and answer list remains as it did before. And now we're running DFS from node C. So node C is going to get turned gray. And we're going to look for white successors of C, but C doesn't have any white successors. And so C is going to get popped off and turned black. And as it turns black, we're going to add it to the answer list right here. And now there's only one node for us to pick, so we're going to pick node B. The answer list remains looking like it did before. And so when we pick node B, B is going to turn gray. And we're looking for white successors of B, but there aren't any white successors of B, so we're going to have to backtrack and pop B and turn it black, which is going to make B, which is going to add B to the answer list. So this is the ordering that we get finally, B, C, A, D, E. And let's just redraw all of these edges to see if this ordering satisfies the prerequisites that we want. So we had an edge from D to E, so that takes care of this edge. We had an edge from C to E, and we also had an edge from C to A. We had an edge from A to D, and that was the only edge from A. And then we had edges from B to E, and then from B to D. So the ordering that we got satisfied everything. And one thing to notice here is that here we had a choice when we were processing B and C. I could have chosen B first and then C. And what that would have done to the ordering here is just switch B and C. But that's perfectly fine because regardless of which one comes first, all of the prerequisites are satisfied. So all of the edges are going left to right. So that's the basic idea of topological sort. Is just run DFS, and whenever a node gets turned black, the moment that it turns black, you just go over here and add it to the answer list. But let's get a bit more of an idea about why topological sort, or why this algorithm works. So imagine that here's this big complicated graph, and we chose one white node to start from A. Now, the white path theorem says that any node reachable from A is going to get colored black before A gets colored black. So that means that as we run this DFS call, DFS is going to reach all of the nodes reachable from A, and it's going to turn them black. And so after this call, we're going to look, the answer list is going to look like this. So A is going to be here, and there's going to be all the nodes that A can reach. So that means all of A's edges are going to be pointing to the right. So then when we pick node B here, we know that any node that's reachable with a white path from B is going to get colored black. And there might be some edges that run from these nodes into these nodes that were previously colored. But what that does is, so this is answer list before, and at the second call, we might sort of visit a bunch of other nodes, and all those nodes get colored black. But what that's going to do is, these edges that are going from the second set of nodes to the first are just edges that go like this. And this is an edge that goes from B to, let's say, one of these nodes over here. So you can see that all the edges are still pointing to the right. And then at the end, maybe we call it on C, and that covers the rest of the nodes. So that's the basic idea about why topological sort is working, is because of the white path theorem. So the white path theorem tells us that anything for which A is a precedent is going to, or a prerequisite, is going to get colored black before A gets colored black, which means that all the edges here are going to go to the right. So this picture also helps us figure out what the runtime of topological sort is. So when you go back and look at the algorithm here, you might say, oh, well, we're potentially running one DFS call for every node. So there's some kind of maybe multiplication going on here. But, and that's totally the right way to think about it, except for the following, that we don't reinitialize the nodes to white, which makes this algorithm much faster. So because we don't reinitialize the nodes to white, even though we're doing multiple DFS calls, every node is going to get visited only once in one of the DFS calls. It can never get visited in two DFS calls because it already got colored some different color other than white. And so because every node gets visited only once, every edge also gets visited only once, because we only look at the edge from the node which is the edge's source. So that's why the runtime of topological sort is just O of n plus m. And again, this is just because we don't, so because we don't reinitialize colors when running multiple DFS calls. So that's the basic idea behind topological sort. So topological sort is an extremely useful kind of algorithm, and you'll see that it comes up in class again very shortly, at least a couple of times. So let's do our last application of graph search here that we're going to call strong connectivity. So the idea behind this application is the following, that we're given a graph G and a node S. And our goal is to find all nodes that have two-way communication with S. So what I mean by this is that both the node is reachable from S and S is reachable from the node. So I think just taking a look at a small example here would be helpful. So consider this example. So let's call these nodes 0, 1, 2, 3, and 4. And here we have a graph. So what are the nodes that have two-way communication with 2? Well, 2 can talk to 3 by sending it a message along this edge, and then 3 can talk to 2 by sending it a message along this direction. And so the nodes that have two-way communication with node 2 here are just nodes 2, 3, and 0. So that's going to bring us to a simple definition here, which is just the strongly connected component of a node S in a graph G are all the nodes U such that U is reachable from S, and S is reachable from U. So when we were saying here that nodes 0, 3, and 2 have two-way communication, what that really means is that the strongly connected component of node 2 is equal to 0, 3, and 2. And the strongly connected component of another node, so the strongly connected component of, let's say, node 1, well, node 1 doesn't have two-way communication with anybody. It can send messages to everybody, but nobody can send a message back to it. So the strongly connected component of node 1 is just node 1, because that's the only node that 1 can talk with. Okay, so let's see an idea about how we might find the strongly connected component of a node. So let's take a look at this example and create our idea kind of based on that example. Okay, so suppose that somebody gave us this graph and they asked us to identify the strongly connected component of 2. The two things that we need to do is, one, find all nodes reachable from 2. And you all know how to do this because that's exactly what our graph search algorithms do. So for example, if we run DFS on the graph G with node 2, and we take a look at the black nodes of this call, what nodes is this going to return? Well, if we run DFS from 2, it's going to color 3 and 0 gray and then black, and then it's going to color 4 gray and then black. And so the black nodes of this DFS call are just going to be 2, 3, 0, and 4. So those are all the nodes that are reachable from 2. But the other thing that we needed to find is we needed to find all nodes that can reach 2. And so there's one way to do this, but it's very inefficient, which is to just try, for example, to run DFS from 3 and see if 2 is in the set of nodes that got turned black. But we can do this very efficiently with just one call to DFS. So the idea is to look at the black nodes of DFS on the reverse graph starting at 2. So let's see what that would do. So let me just draw the reverse graph of what we have up there. So this edge is going to go back. This edge is going to go back in the opposite direction of where it was going. And then this edge is going to go back in the opposite direction. So this was 2, 3, 0, and 1, and this was number 4. And so if we look at the black nodes on the reverse graph, starting at 2, what's DFS going to do? So it's going to turn this gray, then it's going to backtrack, it's going to turn this one gray, backtrack, and so forth. And so the black nodes here is just the set 2, 3, 0, and 1. So those are all the nodes that can reach 2. And that's because a path in the reverse graph from S to something, so a path from S to U, let's say, in the reverse graph, this means that there was a path from U to S in the original graph, because all the edges flipped here. So that's the idea of our algorithm. We're going to run 2 DFS calls, and we're going to swap the graph edges around in the middle. So let's see exactly how that works. So this is our strongly connected component algorithm. It takes in as an input a graph G and a node S. And this algorithm just works like this. So let A be the black nodes of DFS on G starting at S. Then we're going to find G transpose in a format that makes successors easy. We're going to let B be the black nodes of DFS on the reverse graph starting at S. And then we're just going to return A intersection B. So I think the first step and the third step are quite clear. But let's talk a little bit about what happens in this middle step. So for this first step, for DFS to run quickly, we have G in something like RBLL or compressed sparse row. And that's because we need successors to be very fast for DFS, and those are the two things that make successors be fast. But to run DFS on the reverse graph, we need successors to be fast in the reverse graph. And for successors to be fast in the reverse graph, that means it's kind of the same as finding predecessors in the original graph. So over here, we need G in column-based linked list or compressed sparse column format. And so this step right here does a translation from RBLL to CBLL, or something like CSR to CSC. And so you remember this from a homework assignment that was in our first homework assignment. So now let's figure out the runtime of everything. So this first part just runs in O of n plus m time, because it's just a single call to DFS. This translation runs in O of n plus m time, so that was our homework problem. And this next call of DFS just runs in O of n plus m time. And then finding the intersection of these two sets, each of which is of size n, just runs in O of n time. And so overall, everything is just O of n plus m time. So also finding strongly connected components is very fast. And so that's the last application of search that we're going to talk about. It concludes class for today. Thanks a lot for listening, and I'll see you all next time.